of functions when they're increasing, decreasing, and constant, and we're going to determine the average rate of change. Think about it like slope when we were in Algebra 2. Okay, that's the key. It's a lot of slope. We're going to use secant lines to determine the average rate of change. We're going to compute velocity or speed, which is just distance over time. So should be a fairly easy section comparatively to 1-3. Here are your new vocab terms. They're not necessarily new, just the way that we've been using them could be new. Okay, so we have increasing and decreasing. The key when we're doing this, we like to look at everything kind of how we read a book. We read it from left to right. So as we move from the negative side of the x-axis to the positive side of the x-axis, what is our graph doing? Is it going up? Is it going down? That is what it's determining. If it's going up and has a positive slope, obviously if it's increasing. It'll be decreasing if it has a negative slope. A constant. Constant is as you move from one x value to another x value, you receive the same y value. So it's really that horizontal. Relative maximum. It's the highest point in the range. Okay, it'll be relative to where it's at, meaning that it'll give you an interval and we're kind of cut down, not looking at the whole graph, or you'll have what's known as an absolute maximum, which is the total absolute highest point in the range that we'll touch, kind of like you'd have on a quadratic or a parabola that is downward. And you have minimum. Once again, it can be relative or it can be absolute. Okay, once again, this is just the lowest area of the range with the rest of our graph above it in terms of y values. Then you have extrema points. Extrema points are critical points where our graph either is decreasing and begins to increase, or it's increasing and then it begins to decrease. So it's kind of a change in the slope. Average rate of change, that is truly slope. You find that by taking y2 minus y1 divided by x2 minus x1. And more or less, we're not necessarily trying to break it down instantaneously at each individual point. We're just trying to summarize it. So, and you'll see that, and in order to do that, we need to draw a secant line. A secant line is a line that bisects a curve at 2 or more points. So these are your vocabulary. Like I said, comparatively, section 1.4 is tremendously easier than section 1.3 in the terms of the amount of work that we have to do. Okay, key concepts. So a function f is increasing on an interval I if and only if for any 2 points in L, a positive change in x results in a positive change in f of x. So you can see we're given 2 points here. We're working on the interval from negative infinity to a positive infinity. Here's x1, here's x2, and as we move right, you can see that our f of x value for 1 is lower than our f of x value for 2, or it has a positive slope. It's increasing as we move from left to right. Okay, decreasing is essentially the exact opposite of increasing. So what a function is decreasing as if we move from left to right on the x-axis and our y values decrease or get closer to the origin or farther away from the origin if we're in the negative side. So we have x1 here, here's f of x1, here's x2, and here's f of x2. And as we move from x1 to x2, you can see clearly that our graph has decreased in terms of y values or f of x values, outputs. And then a function is constant on an interval if and only if for any 2 points, a positive change in x results in a 0 change in f of x. So we have x1 here, we have x2 here. Our interval is from a to b. So that's just this given interval here. And as we move right from x1 to x2, you can see there's no change in our output values or our y values. So it's really a little bit of common sense. Analyzing it graphically, you're going to be able to see it, but they're going to ask you to prove it. Okay, once again, when we're graphing, it's always an estimation. So we're going to be asked to prove these numerically or algebraically by building a table of values. Okay, to support it, and you'll get in the habit. Most of pre-calculus, they want us to support everything with a table. So analyze increasing and decreasing behavior. It says use a graph of the function f of x, which is equal to x squared minus 4, to estimate intervals to the nearest 0.5 unit on which the function is increasing and decreasing or constant, and support our answer numerically. So once again, technology makes our life easy. For anything that they don't give you a graph on, remember that you have 3 different ways to graph it. We have Desmos, which I'm going to be using right here. You have the TI-83 graphing calculator, this beautiful device here, or you all should have downloaded, if you don't have the calculator, this app on your phone, that Calculator X, because there are areas within this section it's going to want specifics. Okay, Desmos is awesome, but it's kind of an estimation at the same time, right? Wi-Fi went out, said lost connection. That's fine, Zariah. Remember that I'm just try to deal with it to the best of our ability. I know internet kind of really is an important thing, but just make sure that if you don't get to see the whole lecture, that you watch the recorded version. Okay, so as we're looking at this graph, and we'll just do it on the slides rather than Desmos, you can see that as I move from left to right, my graph is decreasing, right? It's going down. Okay, but then I hit the origin point of 0. That would be my relative minimum, and then I begin to increase. Okay, so graphically, it's very easy. We want to look from left to right, and what is our graph doing? It's going down, and then it's going back up. Okay, in this area, there doesn't appear to be anything where it's constant. Okay, but to support our answer numerically, we have multiple options. Technology can make our life easy here, or we can do it manually, algebraically. Okay, and to support it, here's our conclusion that we got graphically. It says from the graph, we can estimate that f is decreasing on the interval from negative infinity to 0 and increasing from 0 to a positive infinity. So again, we saw that pretty clearly on our graph, right? As we went from left to right, it went down. We hit the y-axis, and then it began to come back up. Okay, but now it's time to support it numerically, and they create a table. Okay, this is where technology makes your life simple. You can pull answers from Desmos, like they had -3. When I click on -3, I get a -2. Why is, there we go. Okay, so they're just plugging them in so that they can to build the table. Okay, all it is plugging in x values to get an f of x value. They plug in -3. -3 squared is 9, minus 4 is 5. -2 squared is 4, minus 4 is 0. Do we have to? You'll have to build a table, Clara. Okay, and it's just supporting it numerically. Okay, we just pick, you want to be real selective with the points. Here, we decided that it switched at 0. So I want to pick points that are closest to 0. -1, -2, 1, and 2 would be sufficient enough to support our conjecture. Okay, so once again, we're just plugging in x values. We're recording what we get spit out. And you can see clearly that f of x decreases until we hit 0, but then it begins to increase again. Okay, parabolas are pretty easy because it has one extremal point. It has one maximum, it has one minimum. Okay, typically will always be the absolute or the minimum. When you're dealing with a function like x to the fourth, x to the fourth can have at most 3 extremal points. So it might have 2 relative maximums and 1 absolute. So you really got to look at your graph to determine how many points we're really going to lose. How many times does it switch from decreasing to increasing and increasing to decreasing? So x squared minus 4, it's a pretty easy graph to look at because we only have one extremal point. Okay, and then we took all that information, we supported our conjecture, and we stated our answer that f of x is decreasing from negative infinity to 0 and increasing from 0 to a positive infinity. Okay, here we have a cubic function. It says use the graph of f of x to f of x, which is equal to a negative x cubed plus x, to estimate intervals to the nearest 0.5 unit at which the function is increasing or decreasing. So analyzing it graphically. Once again, we want to move from left to right. And as we move from the left to the right, you can see our graph is decreasing, decreasing, decreasing. And then right about negative a half, negative 1, because it wants us to estimate to a 0.5 unit, probably about a negative half, it begins to increase again. But then we hit 0.5 and then it begins to decrease. So this one has two extremal points here and here, where we were decreasing, then we begin to increase, and then we begin to decrease again. So this one, our table's got to be a little bit more, I'd still want to be strategic with the points that we're plugging in, but our numbers, we're going to have more because we just simply have two extremal points. So from the graph, looks like from negative infinity to a negative 1/2, we're decreasing, increasing from negative 1/2 to 1/2, and decreasing again from 1/2 to positive infinity. Once again, because it has two extremal points, 2 points where it switches from decreasing to increasing. Okay, to support this numerically, we're going to do the same thing. We're going to create a table and we're going to plug them in. So here is their table to support from negative infinity to, that should be a negative 0.5 on their interval notation. They did it wrong. But you can see once they're plugging in these x values, it is clearly decreasing. We go from 24 as an output to 13 to 6 to 1.875 to 0 to a negative 3.75 or 0.375. Then for our negative 1/2 to 1/2, this is the area where we said it's increasing. Okay, so we're decreasing and then we're increasing. So we plug in negative 0.5, we got a negative 0.375, 0, 0, and then 0.5 to 0.375. And then here's our last interval where we said it was decreasing. So we start at 0.375, we go to 0, negative 1.875, negative 6, negative 13.125, and 24. Okay, I know it seems like a lot of work to plug all these in, but use your technology. Okay, use the technology that's available to you. There's no reason why we necessarily have to plug all of these in there algebraically. Okay, you can do that by using Desmos and just tracing your graph. The favorite that I have is obviously the TI-83 because it allows me to plug in certain numbers. Okay, or you can use the graphing calculator that you should have downloaded to your phone. Technology makes you efficient. Okay, technology makes you efficient. They used 0.5 units when they're plugging in their values because we ended up switching at a 0.5. Okay, so make sure that we're being strategic with the points that we plug in. We definitely want to stay close to our extremal points, but there's no reason to go too far outside of our extremal points. And our estimate that we got from the graph was supported by our table. So we can say that it's decreasing from negative infinity to negative 1/2. And from 1/2 to a positive infinity, and then it was increasing on the interval from negative 1/2 to 1/2. But like I said, we saw that pretty easily on the graph. So here we have a graph, 2x squared plus 3x minus 1. We want to estimate intervals to a 0.5 unit, which the function is increasing, decreasing, or constant. So again, we want to look from left to right. As we move farther, as we start here and we move farther to the right, it looks like it stops decreasing right about -1, and then it begins to increase. So it looks like our answer should be B. No, not B. C. F of x is decreasing on -infinity to a -1 and increasing on -1 to a positive infinity. Okay, so you're going to get a lot of good information by analyzing this graphically. You're just building the table of numbers to support it. Okay, relative and absolute extrema. So a relative maximum of a function f is the greatest value f of x can attain on some interval of the domain. Okay, relative means that it's going to be close. Okay, the points surrounding it. So if we're looking at point A here, this would be a relative maximum because these points were clearly higher than it. Okay, we're clearly higher than it. Oh, why did we do that? Stupid technology. But you can see that we're higher than all of these points. It's not an absolute maximum because as we get closer to the point B, you can see that it's definitely higher in the range. So what makes a relative maximum an absolute maximum is if it's the greatest value the function f can attain over its entire domain. Okay, so you have relative, which is just an extremal point where we switch from increasing to decreasing, but the surrounding points are lower than it. It's absolute if it's the highest point in the domain, in the entire domain. So you got to break it down from an interval to the domain. Okay, and then a relative minimum is the exact same thing. Okay, just it's the lowest part in the range. So here, this point A, f of A, would be a relative minimum because it's lower than the points that are surrounding it. Okay, and then we'd have a relative maximum, we'll call that A 0.5. And then we'd have an absolute minimum at the point B because this is the absolute lowest point in the range over the entire domain of the function. Okay, and once again, we're going to analyze these graphically, and then we're going to support it with a table of numbers. Okay. So estimate and classify the extrema of the nearest 0.5 unit of the graph, support your answers. So once again, we want to look at it using left to right. As we move left on the x-axis, starting, it looks like we're starting about -2. Okay, and we move down, and it looks as if somewhere around -1, -1.5, we have a relative minimum. Okay, this would be a relative minimum because this portion of the graph continues down to a -infinity. Okay, once again, use technology to your benefit. I would plug this into your graph, that your graphing calculator or Desmos. That way, one, it's going to make you faster when you're building your table of values. And sometimes the pictures of the graphs in the book are not as clear as we wish they were. So we're decreasing, decreasing, decreasing. The difference between relative and absolute. Okay. So relative is just over a specific interval, whereas absolute is the entire domain. So if we're looking at this one right here, relative is just a section of surrounding points. Okay, a section or an interval of surrounding points. So that's why A would be a relative maximum, because it's a high point, but it's not the absolute high point. Okay, so relative would happen here because it's higher than these points surrounding it. B is the absolute maximum because it's the highest point within the domain. So the difference between relative and absolute is simply looking at the entire graph versus just a section of the graph. Okay, relative, you kind of squeeze down the section and you're only looking at from, say, -1 to 1. Whereas absolute, we're looking from a -infinity to a positive infinity. Okay, so absolute is the whole graph or domain. Relative is just off of a selection. So once again, we're decreasing here, right about -1, -2.2, it'd say. Okay, because we're counting by twos. You can see we hit a low point. This would be our relative because it's lower than the points that are surrounding it. Between -2 and 0, this is the lowest point, right, on those x values. Is it the lowest overall? No, because if we look at our right tail, our end behavior as x goes to positive infinity, you can see that our graph goes to a negative infinity. So that's going to continue without bound, and we have to assume it continues without bound. So we have a relative minimum here. We go up, we have a point of inflection where we change from concave down to concave up. And then we hit 2, and this would be our relative maximum. Okay, once again, relative because our graph continues without bound to a positive infinity as we're looking at left end behavior. Okay, so here we have a relative minimum. Here we have a relative maximum. We cannot say either of these are absolute because the farther we go left, our graph goes to a positive infinity, and the farther we go right, our graph goes to a negative infinity. So there are lower numbers. It's just on the given interval. Okay, relative, remember, we're looking at a section of the graph rather than the graph at a whole. So it appears that f of x has a relative minimum at -1 and a relative maximum at x equals 2. It also appears that the limit as x approaches negative infinity, f of x is equal to positive infinity. So that's talking in behavior right here, left end behavior. As x goes to a negative infinity, f of x goes to a positive infinity. And the limit as x goes to a positive infinity, f of x goes to a negative infinity. So we can conjecture that this function has no absolute extremum, okay, or no absolute maximum or no absolute minimum. That's because, once again, our left tail continued to go up and our right tail continued to go down. So we want to build a table around -1 and 2 to support that we have a relative maximum and a relative minimum. So you can see they've counted by 0.5s. So here's -1. When we went to -1.5, we got -5.9. When we plugged in -1 to our equation, we got -7. When we plugged in -0.5, we got -2.7. So since this at -1, -7 is less than -5.9, which is also less than -2.7, these 3 points right here confirm that this is a relative minimum. It's lower than the points that are surrounding it. They plug in a -100 to show that our graph continues to a positive infinity because we had the left end and right end behavior. Okay, so then our point 2, where we said we had a relative maximum. So when we plugged in 2 into our equation, we got 14. When we plugged in 1.5, we got 8.2. And when we plugged in 2.5, we got 9.8. So 14 is greater than 9.8, and 14 is greater than 8.2. So within these 3 points, or this given interval, this is our relative maximum. Okay, once again, because our left end behavior continued and in opposite directions, we have no absolute. Okay, so in the final answer, that's all just them explaining it. To the nearest 0.5 unit, there's a relative minimum at x equals -1 and a relative maximum at x equals 2 with no absolute extrema. So no absolute minimum and no absolute maximum. I only got like 20 minutes left. Okay. So here's one that they're going to ask us, and I think there's a couple problems like it within the homework. More or less, what it's asking you to do is do the same thing that I've told you to do. Okay, so it says approximate to the nearest hundredth the relative or absolute extrema of f of x, which is equal to x fourth minus x to the fourth minus 5x squared minus 2x plus 4. State the x values where they occur. So the first thing that they do is they've plugged it into their graphing calculator and they've clicked to graph. Okay, and from this graph, you can see it looks like we have a relative minimum here. Looks like we have a relative maximum here. Looks like we might have an absolute minimum here because our graph continues on both ends to a positive infinity. And then they want you to use the trace function or the calc function. Okay, to access the calc function, you'd hit second trace and it's going to spit out, it's going to bring you to like a table of values. 3 and 4 on the calc menu, 3 is minimum and 4 is maximum. Okay, so we'd be able to use our graphing calculator to actually find our maximum and minimum values. Okay, here's them explaining the intervals. Once again, from -2 to -1, looks like there's a relative minimum, a relative maximum between -1 and 0, an absolute minimum between 1 and 2. Okay, the end behavior of the graph suggests that this function has no absolute extrema. That's false. The end behavior shows that we have an absolute minimum. Okay, so using the minimum and maximum selection from the calc menu of your graphing calculator, you can estimate that f of x has a relative minimum of 0.8 at the x value -1.47, an absolute minimum of 5.51 at x value 1.67, and a relative maximum of 4.20 at the x value -0.2. So once again, this is just using the calc menu. The TI-83 makes it fairly simple. What you got to do is it's going to ask for a left bound and a right bound. Just make sure that you're to the left of your extrema point when it's asking for the left bound, and to the right of your extrema point when it's asking for the right bound. And then you click enter to select those points, and then click enter a third time because it's going to ask you to guess to get an official answer. Once again, you can do all of that using Desmos, okay? Using Desmos.com, and instead of using the calc button, we would be able to just click on the points. Okay, click on your graph, you can drag and hold it that way, and you can get a pretty good approximation. Let's get to our next thing. Okay, average rate of change between any 2 points on the graph of f is the slope of the line through these points. So you can see this red line here. This is what's known as a secant line. It's a line that intersects a curve through 2 points. Okay, or a line that intersects a curve at 2 points. So, and then you can see how we calculate it. F of x2 minus f of x1 is divided by x2 minus x1. Okay, you've seen this equation 100 times on Algebra 2. It was just always called the slope. Okay, so they use it in function notation as f of x2 minus f of x1 over x2 minus x1. Okay, what we have to understand is that this is equivalent to y2 minus y1 over x2 minus x1. This is just the function notation. This is the way that you probably had the most experience with it, but it's just the slope formula. Okay, it's the formula to find slope. Okay, so when they're asking for average rate of change, it's nothing too difficult. It's nothing that we haven't done before. Okay, and then they'll ask for speed, which it's still just finding the slope. Just speed by any other definition is distance divided by time. So like miles per hour, feet per second. But it's all slope. Average rate of change is all slope. Okay, so we have a secant line. Okay. So to do this fast, we're going to do this using Desmos. So I have negative 2x squared plus 4x plus 6, and I'm on the interval of negative 3 to a negative 1. That negative 2x squared plus 4x plus 6. And we are on the interval from negative 3 to a negative 1. Perfect. So here's negative 2. Count by 5s, 0.5. Just step by ones. There we go. Now I can see it. Okay, the cool thing about Desmos is you can zoom in, zoom out. Okay, but negative 3, it's this grid line, and you can see that it's going to fall way down here. Take it left, take it left. Negative 2.7. Negative 3, negative 24. Okay. Okay, once again, they're just plugging negative 3 into that equation. We can do that algebraically, but it's not always the best thing. So we plugged in negative 3, we got a negative 24, and we want to find where it's at negative 1. This is probably my one complaint about Desmos. I love it because it gives you all access, but at the same time, it kind of makes it a little difficult to find your given points. This is much easier when you're using like a graphing calculator, okay, because we could just punch in trace negative 3, trace negative 1, get our y values. Okay, so we plugged it in. We've got our functions. We were given negative 3, negative 1. So we would draw a secant line between those two. Okay. And our secant line, you can see it would go from negative 3, 24, negative 24, all the way up through negative 1, 0. So now it's just time to fill out our slope formula. Okay, that's them filling out the slope. I went a little too far. So f of x2, they're using negative 1. F of negative 1 is 0. So we would have 0 minus a negative 24 over negative 1 minus a negative 3. Okay. And like I said, we're just doing the slope formula. Hardest part of that using Desmos was just finding the points. So a 0 minus a negative 24 yields 24 on the top, because when you minus a negative, you're really adding. And negative 1 minus a negative 3 is going to give you 2 on the bottom. So we'd end up as 24 halves. Okay, 24 halves would simplify down to 12. And that is what we would say is our average rate of change between negative 3 and negative 1. You can see they've given us our brackets, they've given us the interval. It's just our job to figure out what is our y values on those given intervals. for -3 and -1. And then we plug it into the slope. Slope formula. God, what is that thing called? Getting better, but I'm still not great yet. Okay, so we've simplified it down to 12. Okay, and that's just the result of our slope formula, which is y2 minus y1 divided by x2 minus x1. And the average rate of change on the interval from -3 to -1 is 12. The graph of the secant line supports this. So you can see that's just them plugging it in, drawing their secant line, and taking the slope of that secant line. So nothing too terribly difficult. The hardest part is getting the y values out. You can plug it in algebraically, a little bit more work, but it might actually be quicker than having to go through what I struggled with on Desmos. The fastest way is going to be using your TI-83 or the Calculator X program. And that's simply because we have the trace function. So our answer here would be 12. So find the average rate of change of f of x is equal to a -2x squared plus 4x plus 6 on the interval 2 to 5. I'm going to do this one algebraically. Okay, you can do it graphically, but lack of a better term, that was a little bit more of a struggle, and I don't really want to do it yet. So first I'm going to find what f of 2 is. So that's -2 times 2 squared plus 4 times 2 plus 6. And I have f of 5 is equal to a -2 times 5 squared plus 4 times 5 plus 6. Okay, 2 squared is 4 times a -2 is -8 plus 8. 4 times 2 is 8 plus 6. So -8 plus 8 plus 6 is equal to 6. So I have the 0.26. Okay, and then I'm working 5. 5 squared is 25 times a -2 is a -50. Plus 4 times 5 is 20 plus 6. So -50 plus 20 is a -30 plus 6 is a -24. And I have the 0.5, -24. Okay, from here, since I have my points, that was just me plugging them into my equation to get my y values. Now I just plug it into the slope formula. Okay, so on the top, I'm going to have -24 minus 6 over 5 minus 2. -24 minus 6 is equal to a -30. 5 minus 2 is equal to 3. And then to simplify this, it would break down into a -10. Okay, simplified form. So 10 is my average rate of change on the interval from 2 to 5. So more or less, we've given a curve. We draw a straight line through it. And then we take the slope of that line. Okay, once again, probably the hardest part is finding the actual points. So when they plugged in 5, they got -24. When they plugged in 2, they got 6. And then that 3 is the result of 5 minus 2 in the denominator. Simplifies down to a -10. There's what it looks like graphically. You can see they've got a point from 2, 6 through 5, -24. The average rate of change is -10. Okay, average speed. Okay, it's the same exact process as what we just went through. Okay, average speed is average rate of change. The thing that makes it speed is that speed is always classified, it has to be, distance traveled. It's a good thing I'm not an English teacher, can't spell. Over time. Okay, distance traveled over time. So when they're asking you to find the average speed, okay, they're going to have a graph where the y-axis is your distance and your x-axis is your time. Once we run the slope formula, okay, because distance is our y values, our slope formula is y2 minus y1 over x2 minus x1. If we were to put this into perspective, this y2 minus y1 is equal to your change in distance. Okay, and this x2 minus x1, since our x-axis is in an element of time, is over the change of time. Okay, and all it is just an average. So that's why whenever you're talking about speed, you always hear miles per hour. Miles divided by hours. If it's feet per second, feet divided by seconds. Okay, speed is always an element of distance traveled divided by the time. Okay, but you can do the same exact process. You're going to draw the secant line. You're going to use the slope formula. Okay.